Hello, and welcome to this video about symmetry as a compositional tracking option in Olga. This video is created by Herbert Lauria and Knut Even Lundsbakken. Let us take a look at a few demonstrations. I will show a brief overview of the different available options to create fluids in Symmetry and how they can be exported to Olga, using fluid files that can be consumed in the compositional tracking option. We can start by opening Olga and then going to the Tools section to open Symmetry. You could see a couple of options, the 32 and the 64-bit installation. In this case I will select the 32-bit option. After I select it, Symmetry will load, and I can start working with it. Now, we can start defining fluids in Symmetry. Fluids in Symmetry can be defined in many ways. The more direct way to do it is by specifying pure and hypothetical components. To do that, we start a new project in Symmetry and then select the thermodynamic model we want to use. Then, we can add some pure compounds, or we can also create hypothetical components by cloning pure components or defining new ones. To define a new hypothetical component, the minimum information needed is a name and the normal boiling point or the molecular weight, and specific gravity. Once all the properties are entered, the component will be added to the list and you can inspect all its properties and the methods used for their calculations. Once all the components are added to the thermodynamic model, you can bring a material stream to the Symmetry case, and there you can define the fluid composition. Another way to define fluids is to use the oil characterization tool. Here you can create fluids based on oil assay data like distillation curves, light ends, and physical properties. The oil characterization tool will create components with compositions that represent only the characterized fluid. If more fluids are needed, then another set of components and compositions will be necessary. Therefore, you cannot define different fluids with the same group of components. If you want to keep a constant slate of components, then the molecular structure characterization is more suitable for your case. In this option, you will need to create a blank slate of components by clicking in the Piona button. This will bring an environment where you can define your component slate based on different chemical families, paraffins, isoparaffins, olefins, naphthenes, and aromatics, and boiling points or carbon number ranges. Once it is done, you can return to the Symmetry case and add an oil source unit operation. Here you can enter different types of laboratory data like distillation curves, compositional analyses, cut ranges, Piona and Sara distributions, and information regarding wax and asphaltene precipitation. Once the data is entered, you can click on the Regress Parameters button to find the best composition from the slate that matches all your data. One more way to define fluids is by importing fluid files from other software. In this case, I will show how to import a multi-flash file from the included examples in Olga. Go to the Import button and click in the Replace button to select the fluid file to be imported. Once selected, click on the Open button and this will bring the fluid information to Symmetry, including the equation of state, and pure and hypothetical components defined in the original fluid file. If desired, the equation of state can be switched from the Thermodynamic Model tab, and the methods to calculate properties in the model can be modified in the Settings tab. The Symmetry case will contain a material stream with the defined fluid composition from the original file. Now, the next step is to export the fluid into a Symmetry fluid file that can be read and used by Olga compositional tracking. To do that, return to the thermodynamic model window and click in Export. You can select a name for the fluid file and saved it in your computer. The Symmetry fluid file will have an extension called THM, which is the one accepted in Olga compositional tracking. Okay, so let's take a look at how this is set up in the Olga user interface. In order to enable compositional tracking, you navigate to Option and select Compositional On. The default option is Multi-Flash. To select Symmetry, you need to add Comp option. This can be done by right-clicking in the case in the model browser and selecting Add before going to Compositional and then choose Comp option. The first option is selecting PVT package, where you can choose to use the Symmetry fluid engine instead of Multi-Flash. You need to select the Symmetry generated fluid file with the extension .thm. This is done in the same way as selecting any fluid file. Note that you need to select the .thm extension to see the file. We select a runtime of 10 hours, and then run the case. We can see that the case is starting up and is running to completion. For further demonstration of compositional tracking with Symmetry, I have also created a simple model of 4 wells and a pipeline. It is a 10-hour simulation, simulating a shutdown of the wells after 2 hours and the ramp-up of the wells starting at 4 hours. The options are the same, with selecting Symmetry engine under Comp option. The case is set up with 2 reservoirs, so the .thm file has 2 streams defined, one for each reservoir. We can see that by looking at the definition of each of the reservoir contact keywords. I have already run the case, so let us look at some results. This plot here is showing the mass flow for each well. As you can see, the production is shut down after 2 hours and starting to ramp up again after 4 hours. Compositional tracking is more accurate than the table approach, especially if you are mixing fluids from several reservoirs and the mix is not constant. But compositional tracking is also more computer demanding than the table approach. In this case, the fluid file contains 32 components, but still, we can see that the speed is 14 to 15 times real time when the wells are producing, and higher during shutdown. This will of course be case dependent. That concludes the demonstration.